All right, so day 3 of notes, evaluating limits algebraically. Again, to recap, day 1 was from graphs. That's usually pretty easy because you're just looking at the picture. And again, you have to think about left limit and right limit. But if they go to the same spot, it's easy. Day 2, that was tables. That was yesterday. Harder than graphs, I guess, but still relatively easy. You're just looking for, are we approaching a number, and is it the same number from the left or the right? Not a big deal. Today, algebraically, I'm just going to say it's significantly more difficult than graphs or tables. But again, graphs and tables weren't hard, so we can be significantly more difficult without reaching difficult. Fair? I hope that's the case. All right, some properties. The good news is all of these properties that we're going to look at for limits make sense. So there's nothing weird about these. They do what you think they would do. They act like you think they should. How's that for a summary of notes? Yeah, it does what you think it ought to do. That means, meaning if you want to add limits, it's okay to add them separately. I mean, there's a fancy way to say that. The sum of the limits is the same as the limit of the sums. But saying it fancy, I don't think makes it easier to understand. Maybe makes it harder to understand. The difference of the limits is the same as the limit of the differences. Same thing with product and quotient. So you can add, subtract, multiply, and divide inside the limit or outside the limit, either way. So, I don't know. We're not going to spend much time on those. They act like you think they should act. Okay. Methods for evaluating limits algebraically. Let me back up and talk big picture for a minute. So, methods. First method, always, always, always try substitution first. And if you get an answer, you're done. Great. Most of the time you won't because that's too easy. Like we want to bump you into the second class of problems where you have to do some algebra tricks. So how to say that? If you get an answer, you're good. If something weird happens, then say if no good answer, talk about what that means in a minute. Then you have to try some of our algebra tricks. And our algebra tricks are factoring, dealing with fractions, and dealing with conjugates. And this is what I meant by saying you've done all of these things. And yeah, at least in theory, you know how to factor, you know how to mess with fractions, you know how to deal with conjugates. So you've done them all, you just haven't done them all with limits. So hopefully your factoring, fraction, and conjugate skills are where they ought to be, and that'll make this go relatively smoothly. But we're going to practice them because you haven't done some of these things in a while. Okay, that's big picture. Now we're going to sort of zoom in and do some substitution problems, and then do some factoring problems, and then some fraction problems, and then some conjugate problems. And so that's why I was saying earlier, like there's a lot to do today, and that's the argument for breaking it up over 2 days. But if you break it up, then you don't see it all at once, and you know it's a forest and trees issue. So hopefully we got a sight of the forest, the overall big picture, and now we're going to zoom in and try some of the individual things. So substitution. Always, always, always try substitution first. If you get an answer, you're good and you're done. So let's plug in 1 and see what happens. 4 minus 8, negative 4. 2 minus 4, negative 2. So my answer is 2. It's like, wow, limits are easy. Except that we don't usually give you the easy ones. Let's skip B and C because it's the same thing. Plug them in, you get an answer, great. Let's try D. plug in 0, cosine of 0 over 3 times 0. Cosine of 0. Cosine of 0 is 1. 3 times 0 is 0. Now be careful. 1 divided by 0 doesn't work. Let's back up a little bit. We're getting closer and closer and closer to 0, right? The limit. So it's not like a firm 0. It really means like really close to 0. And what's 1 divided by really, really, really close to 0? 1 divided by a really small number. A really big number. Like infinity. So infinity and d/e, they're not the same thing. Infinity is a subset of d/e. If it's infinity, that means it does not exist. Sine of x over 7. So if I plug in 0, I get sine of 0 over 7. Sine of 0 is 0. What's 0 divided by 7? That one's just 0, so that one's fine. That one's okay. E to the x over natural log 2 as x goes to infinity. Okay, plugging in infinity seems a little bit weird. E to the infinity over natural log 2. What kind of number is e to the infinity? Like big or small? Pretty big number. So if I got a really big number divided by natural log of 2, and they're not just big, but like big and getting bigger, like we're headed to infinity, divided by natural log 2, well, I don't know what natural log 2 is, but this just keeps getting big, 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 so that we're still headed for infinity for that one. And then g, 1,000 divided by 2 infinity minus 4. Again, you can't technically plug in infinity, but that's what you're doing in your mind. 2 times infinity is really, really big. Minus 4 doesn't really do anything, right? 2 gazillion minus 4. Roughly 2 gazillion. So 1,000 divided by really, really big and getting bigger. What are we headed for here? 0, right? This is the, if I had $1,000 in my pocket and divided it equally among everybody in the world, everybody's getting $0. Okay, when evaluating a limit, try to plug in the x value. If you get like something real over 0, then your limit is infinity. Like that happened. That was D. If you get a non-zero real number over infinity, so 1,000 divided by a really big number, this was G, then your limit is 0. I don't think these are things you memorize. These are things you think about when they show up. 0 divided by anything is 0. Okay, that makes sense. That was example E. And infinity divided by not 0, that was example F. Really, really big number divided by 7. Well, dividing by 7 is nice, I guess, but you're still going to infinity. These are not things you memorize. These are things you think about and figure out when they happen. Okay, and that's not even the weird cases. The weird cases, more interesting is a fancy way to, or a nicer way to say that. The weird limits are when we get an indeterminate form. In fact, we've been doing this in calculus the last couple of days. Indeterminate form when we plug in the x value. Indeterminate forms are 0 over 0, infinity over infinity, negative infinity over negative infinity, because you don't know what you're going to get, right? If I have a really small number divided by a really small number, well, it's like, well, which one is smaller and which one is bigger? Well, it's hard to tell if it's just 0 over 0. Same thing with infinity over infinity. Is that infinity because it's getting bigger, or is it 0 because we're dividing by infinity, or does it just 1 because they reduce? And like, it depends. Like, how big are the infinities? That's why they are indeterminate. There are other indeterminate forms. And basically indeterminate forms is when you have like conflicting rules, like 1 to the infinity. Well, 1 to anything is 1, but weird things happen when you're going to infinity. And what if it's not 1? What if it's like 1.00001? Well, then you're getting bigger. 0 to infinity, same kind of thing. 0 to anything is 0, but what if it's not quite 0? What if it's like 0.00001? Some other weird things. The only ones we're going to have to worry about are those. For right now, those are the only ones we're going to worry about. So we're going to substitute. If we get one of those, then we have to jump to one of our algebra techniques. If you have a rational expression and you get 0 over 0, that means you have a hole in the graph, right? That meant there was factors that could have canceled. In fact, that's where we'll get the factoring part. You must have strong factoring skills in calculus. Well, yes. Again, you always try substitution first, because you may not need to factor and reduce. And in calculus, if you don't try substitution first and you go to a secondary method, it might lead to a wrong answer. So you've got to try substitution first. So if I square -2, I get 4. -4 times -2 is +8, minus 12. Over 4 minus 4 is 0. So that's 0 over 0. Be careful. Do not write equals 0 over 0. Because it doesn't equal 0 over 0. It equals some number. We don't know what it is yet. But if you write equals 0 over 0, that's an incorrect statement. Like, I know what you're doing. I know what you're trying to do. But that's an incorrect statement. If you accidentally put equals, then go back and just mark it out. Like, oh, wait a minute. It can't be 0 over 0. I've got to figure out what this is. So let's factor. This is an easy one.
0, 0, 0, 1.
That's why it's indeterminate. Is 0 over 0, is it 0? Is it 1? Is it infinity? Or is it something else? Let's figure out what this one is. Let's see. 6 and 2 would make 12. X minus 6, x plus 2. And then in the bottom, x plus 2, x minus 2. Which is nice. Like, if it's a factoring one, there's going to be like a sort of a built-in hint that the factor should cancel. So that should help you factor. Like if nothing cancels, then you probably factored wrong. So let's try again. Now let's plug in -2. So that would be -8 over -4. Okay, that gets me like a real number 2. So in this case, 0 over 0 equals 2, which is weird. That's why 0 over 0 is indeterminate, because you shouldn't say 0 over 0 equals 2. Okay, all of these are kind of the same. So let's skip B and C, but let's do D. I plug in -3, I get -27 plus 27 over 0. So that's indeterminate. Oops, put that where you can see it. So let's factor and hope that our factoring skills, and maybe now you realize why I picked D to do. It's a sum of cubes. Do you remember how to do a sum of cubes? Soap. Now be careful with soap. Like, soap is great, but soap only tells you the signs, right? So same sign, opposite sign, always positive. You still got to figure out the numbers. So x plus 3, right? Because this is 3 cubed, or excuse me, x cubed and 3 cubed. And then square the first one, multiply the two together, square the second one. So most people remember soap. So it's not the signs that are an issue, it's the numbers other than the signs. Alright, x plus 3's will cancel. And then let's try again by plugging in negative 3. So that would be 9 plus 9 plus 9 would be 27. So in this case, 0 over 0 equals 27. Again, that's not a true statement. I shouldn't say it that way. Let's see. Why don't you try E, and then we'll move on to the next section. Try E. Okay, so there's the answer to E, 1/3. Again, factor, cancel, and then try again. Okay, so this says 3, but it's really like method 2 if the substitution doesn't work. Simplifying a complex fraction. Okay, and different people do this different ways, but to me the easiest way is to multiply the top and bottom by a common denominator. Because that will clear all denominators. And if we clear all the denominators, then we don't have a complex fraction anymore. We got a simple fraction, and hopefully that should work. So we're going to spend a little bit more time on these because I feel like our fraction skills might not be as good as our factoring skills. Maybe I'm wrong. So part A, what could I multiply the top and bottom by that would clear out all the fractions? It's an easy one. X. So if I multiply the top by x, that'll cancel that x in the bottom. Obviously, you can't just multiply the top of a fraction without multiplying the bottom of a fraction. Oh, wait a minute, I need to back up. I do this all the time, and students do this all the time. Substitute first to see if you get an answer. Now, all of these are in the simplify a complex fraction like section of the notes, so you're going to have to do it. But if they're just like walking around in the wild, you don't want to try this until you've substituted first to see that it doesn't really work. So if I plug in negative 5, I would get negative 1 plus 1 over 5 minus 5. I'm intentionally not writing equal signs. So yeah, that one doesn't work. Again, I'm probably going to slip up and not do that because I know that they're not going to work. But I should try substitution first every time. Okay, back to multiplying through by x. So first term, the x's cancel. That's why we multiplied by 5. Second term would just be plus x. And then in the bottom, I think I'm just going to leave it as 5 plus x times x. Because kind of like with factoring, I do want something to cancel. So there is a similarity with, with all the algebra methods. And that is, after you do your algebra magic, something cancels. And in this case, the 5 plus x cancels. Be careful, that still leaves a 1 in the top. And if I now substitute negative 5, I get negative 1/5. Okay, again, so today there's definitely big picture and small picture things going on. Big picture is weird limits, indeterminate form, you have to do an algebra method. Small picture is which algebra method do I use, and can I do the algebra method without messing up the algebra? If I plug in 2, this time I remember to do it first, I get 1/2 minus 1/2, that's 0. 2 minus 2 is 0, so yeah, this isn't going to work. I've got to try something. What could I multiply that would clear all the denominators? 2x. So let's multiply the top by 2x and the bottom by 2x. So So in the top, on the first term, the x's cancel, leaving 2. On the second term, the 2's cancel, leaving x. And in the bottom, I probably don't want to multiply because I'm hoping something will cancel. Oh. Nothing cancels, kind of. Something is going on here. Like I can't cancel right now. So if you just want to say nothing cancels, that's fine, but then I'm still stuck with 0 over 0. Go ahead. So, yes, let's factor out a -1 from the top, or the bottom, but the top would make more sense. If I factor out a -1, what goes in the parentheses now? Yeah, I'm hoping you'll see what we can do to make it look the same. I mean, you can write it as -2 plus x, but that's the same as x minus 2. And if you write it as x minus 2, then it's a little easier to see that it will cancel. So you can certainly write it as -2 plus x, but the whole point was to switch the order so that we could cancel. Now let's back up a second and save ourselves some time in the future. Whenever you have subtraction and the order is reversed, that will always cancel to not quite, unless I heard you wrong. Think about 5 minus 3 over 3 minus 5. -1. It'll always be -1. So some people are going to skip this step. That's the official math step. But after you've done it 2 or 3 times, you're like, wait a minute, I'm always getting a -1 out of that. And so some people will say, you know what, I can just cancel that and cancel it. I shouldn't say cancel it. That always reduces to a -1. So you can show the work. You don't have to show the work, whichever. Okay, back to trying x approaches 2. Well, this is easy now. -1/4.
Did we ever substitute at the beginning?
I did. I didn't show my work. But I substituted and said 1/2 minus 1/2 is 0. 2 minus 2 is 0. That would be one where you don't really have to show your work, because if substitution would have got you a correct answer and you didn't do it, then you're off on the wrong track. Part C. Substitution for Kate's benefit here. Let's see. 5 over 5 is 1. 4 over 4 is 1. And 3 minus, yep, that's 0 over 0. So now I've got to do my, again, it's in the simplify complex fraction portion of the notes, so you're going to get 0 over 0 on all of these. Oh, this is going to be kind of ugly. What do I need to multiply by to cancel out all the denominators?
Plus 2 and x plus 1.
Yeah, both of them, x plus 2 and x plus 1. Okay, so on the first term, you know what? I hope this isn't necessary, but I'm going to do it the first time. I'm going to write out everything to avoid canceling the wrong things. You're probably not going to do this past this time, but I'm going to do it this time. I hope you think this is overkill, but some people need to see it, and that's okay. So I put x plus 2 times x plus 1 on everybody. Again, some of you are going to skip this step after we've done 1 or 2 of these. So on the first term, the x plus 2's cancel, and that leaves me with 5x plus 5. On the second term, the x plus 1's cancel. Let's be careful with that negative. So negative 4x minus 8 all over. And again, the point of these is to cancel something out, so I am not multiplying out all of that stuff. That would be a mess. I'm going to leave it and hope that somebody reduces. And in fact, once I've done a bunch of these, I start getting a hint. I'm pretty sure that x minus 3 needs to go away so that I don't have a 0 in the bottom. So I'm thinking that x minus 3 is going to go away, but let's see what happens. 5x minus 4x is x. 5 minus 8 is negative 3. And sure enough, adios to x minus 3. One of my favorite algebra mistakes is to cancel that and then not really pay attention and forget that you have a numerator, right? Like, no one's going to do that. Now let's try to plug in 3 again. So this is 1 over 5 times 3 plus 1 is 4, so 1/20th. Lots and lots and lots of algebra. All right, let's pass on D because it's kind of the same thing. What would you multiply by? I guess just tell me that and then we'll move on. X plus 1, x plus 2. And so it's really the same kind of problem as part C. So let's bypass that one. E. What do you think we should multiply by on E? 2x. Oh, you know what? I also skipped substitution. But it doesn't take long. So 10 over 10 minus 5 over 5. Yep, that's 0 over 0. I'm going to pause. You see if you can finish out E on your own. So multiply top and bottom by 2x. So I get 10 minus 10 in the top. That's 0. Okay, now this is where things get a little bit tricky. If you plug in 5, it seems like you get 0 over 0. Do you know why I'm saying seems like? Distribute
the 2x to the x minus 5.
I'm still going to end up with 0 in the bottom. Right? This is tricky. This is x approaches 5. It's getting really close to 5. But this top number is like a firm 0. That's not like close to 0 or almost 0 or a little bit more than 0. That is like a hard 0. That is a definite 0. This bottom number is like getting close to 0, like really close to 0. And usually that makes things blow up and have a problem, but like if I have $0 in my pocket, this isn't going to work. If I do 0 divided by anything, it's still 0. Okay, so be careful on this one. You think it's 0 over 0, which doesn't work, but it's not a limit 0. It's like a hard 0 over a limit 0. Does that make sense? Yes or no? Say no. I don't know if there's terms for that, but it's like a hard 0, a definite 0, divided by, well, it doesn't matter, almost 0. It's still, this is 0, which is what some of you got right away.
How do you know it's close to 0 and not a hard 0?
Okay, 10 minus 10, that's 0. There's nothing limit in the top. I'm not plugging in anything and getting like almost 0. In the bottom, though, I'm plugging in. I say I'm plugging in 5, but remember, I'm not really plugging in 5. I'm plugging in 4.9 and 4.99 and 4.999 and 4.99999. And so I'm getting really, really close to 0, but that top number is a hard 0. It's not a close to 0. It's a firm 0, a definite 0. I don't want to say absolute 0. That sounds like chemistry stuff. Okay, so that one's kind of tricky. F, what would you multiply by on F? And then we'll move on. What would clear out all the denominators? x plus 2, and 9 minus x. And I think you would leave the top alone because you don't want to cube all that stuff out. In the bottom is where you would hope things clean up, and you would hope the x minus 2 cancels because that's what's making a 0. So we'll leave that one alone. That one works out a little more normally. So E is definitely the weird one, that idea of a firm 0 over a limit 0.
So could you just think of it as like 0 over 1 over in like infinity? Because that's basically what this is. It's getting infinitely close to 0.
Mm-hmm.
So it's 1 over infinity.
Right. So that's not 0. That's close to 0, but it's not 0.
Oh,
But the top is a definite 0. I don't know how else to describe that 0. A hard 0, a definite 0, a firm 0, 0, 0.
well, it is 0. It's just the other one isn't 0.
That's maybe a better way to say. The bottom one is close to 0 or not quite 0. So that's the tricky one. Okay, so we've covered 2 algebra methods. So let me back up and talk big picture again. Substitution first, unless you're being lazy like me. If you get one of the indeterminate forms, then you either factor and reduce, fraction and reduce, or conjugate and reduce. Factor, fraction, conjugate. And the good news is you almost always know right away which one to use, because fractions are obvious and conjugates are obvious, because the conjugates usually have a square root. There's some signs in here, so I need to be careful about that. But usually it's pretty obvious when you need to factor, because that's polynomials, when there's fractions, and when there's conjugates. So like picking which method is not part of the difficulty. It's just like executing the method is the tricky one. Okay, so let's do, don't really want to do all of these. Let's do A, C, and D. Those look similar, but they're going to lead to different results. And then E. So we'll do 4 of them. Okay, again, you plug in first. Square root of 16 is 4. 4 minus 4 over 16 minus 16. That's 0 over 0. That doesn't really work. Okay, so what conjugate do you think we should multiply by?
X plus 16 or x.
Okay, so there's your 2 options. X plus 16 is a conjugate of the bottom. Square root of x plus 4 is a conjugate of the top. So like, how would you know which one to multiply by? You always pick the one that has a square root in it. Fix the square root. So, Dia, put you on video. You were right. Well, you're on video being right. Isn't that good? So multiply top and bottom by square root of x plus 4. Let's see. So we FOIL the top. That would get us x. And then, as always with conjugate, the O and the I go away. That's why we multiply by a conjugate. So minus 4 root x plus 4 root x go away. If you want to write those out, you may. I'm going to pass. Oh, and then, hey, that was nice. In the bottom, I definitely do not want to multiply that out, partially because it would be ugly, partially because I want it to cancel. So when you multiply by the conjugate, pick the square root one, and then only multiply out the square root one. Leave the other one factored, because cancel out. Limit as x approaches 16. And then try again. Like, that's the whole point on all of these. Like, do your algebra trick, and then try again. Meaning substitute again. 4 plus 4, that's 8. So 1/8. I don't want to do B, but I want you to tell me what you think we would multiply by. So it's definitely the bottom one. Square root of x minus 1 plus 2. And then you would not actually multiply out the top because that would be a mess. You would actually multiply out the bottom and things would go away. Yeah, we'll hit one on E that covers that difficulty level. So let's skip the rest of B and go to C. So if we plug in 0, we get cosine of 0 is 1, sine of 0 is 0. All right, we got a problem. All right, well, conjugate of this, there's really only one option here, I think. What do you think we should multiply by if we're in the conjugate section of the notes? Victoria, I think you were about to say it. I think it was right.
Cosine of x plus 1.
Yeah, cosine of x plus 1. Like, that's kind of the only option that has a conjugate there. So let's try cosine of x plus 1. And again, multiply out the conjugate piece, because that's the whole point, but don't multiply out the non-conjugate multiplying, because that should cancel. Okay, so cosine squared minus cosine plus cosine goes away. I'm not writing it down. Minus 1 over sine of x times cosine x plus 1. Because again, we're not supposed to actually multiply the non-conjugate multiply. Factor. If we factor the top, we're going to end up right back where we started. Right? Is that what you're saying? Like if we factor this into this, then they cancel and you're right back where you started. So not a bad idea, but it would be spinning our wheels at that point. If only there was some equation or formula that related cosine squared and 1, those trig identities. Sine squared plus cosine squared is 1. Like that's the way I memorize it. I can rearrange things, but sine squared plus cosine squared is 1. So cosine squared minus 1 would be positive or negative sine squared? Negative sine squared. Okay, so now one of the signs will cancel. So negative sine of x over cosine x plus 1. Okay, so we got something to cancel. That means let's try again on the substitution. Sine of 0 is 0. Uh-oh, I'm worried. Cosine of 0 is 1. Okay, we're fine. 1 plus 1 is 2. And 0 divided by 2 is 0. Why don't you try D? Try D. And I kind of warned you already that they're obviously similar, but they lead to different answers, so there's your hint on D. So 1 minus cosine squared is equal to sine squared. So one of the signs will cancel. And I've got 1 plus cosine over sine. And then I'll plug in 0. So let's see, 1 plus 1 is 2 over 0. Uh-oh. It's not 0 over 0, so there's not anything to fix. If I'm dividing by 0, well, I'd have to really think if it's positive or negative infinity, but either way, it's D and E. I don't know which one, positive or negative, but I don't need to. It doesn't work. Okay, so 0 in the bottom with a regular number in the top doesn't work. All right, let's try one more. Just because there's lots of square roots in that one, although it's really not as bad as it might look. So square root of x plus 2 minus square root of 2. So I'll FOIL the top, I'll leave the bottom alone and hope that something cancels. So,
Minus or plus?
oh, it should be plus. Yes, thank you. I even put it in red to highlight the difference and then messed it up. So what's root x plus 2 times root x plus 2? X plus 2. The middle terms, the O and the I of FOIL, when we have a conjugate, cancel each other out. So you could think through it and write it out, but it cancels each other out. Root 2 times root 2 is 2, so that's pretty nice. That'll go away. So the 2 minus 2 goes away. And then the x over x goes away. And now I get to try again with my substitution. So that would be 1 over root 2 plus root 2.
Good morning. Matt Ashley.
Which is 1 over 2 root 2. And we are done.